Alright, hello everyone. I hope you guys are doing good. So today I'll be discussing the solutions to Codeforces Round 768. So this was the Division 1 plus Division 2 round and it ended like an hour ago. Even though I didn't officially participate, I was trying out the problems side by side because I'm slightly unwell right now. So yeah, today I'll be discussing the solutions to the first 4 problems of the Division 2 round from A to D. And before that, let's talk about the round first. So according to me, this round was definitely on the trickier side. Maybe it's because I didn't participate officially. That's why I'm finding it a bit difficult because I didn't give much thought to C. And like mostly because of problem C, I found this round a bit challenging because the solution to problem C is not very evident. It is a weird constructive problem in which the solution is not very intuitive. You have to think about a lot of cases to come up with the AC solution. And yeah, that's more or less it. Also, problem D is very nice. I found it really beautiful. So yeah, all in all, a good round, but problem C could have been a bit better according to me. Right. So yeah, without any further ado, let's start with the solutions, and I'll be discussing solutions from A to D. Let's start with A. So in this problem, we have two arrays A and B of n positive integers, and we can apply the following operation on them any number of times. So we can select an index I and swap AI and BI. That's the only thing which we can do. And we can do this operation any number of times that we want. And what we need to tell is we need to tell the minimum possible value of maximum element in A multiplied by maximum element in B. We can apply any operations any number of times that we want, but finally we want to minimize this value, which is the maximum value of the product, which is the maximum value of the product of the maximum element in A and the maximum element in B, and the minimum value of that. So yeah, that's the problem, not very difficult to think about. Let's see how to solve it. So the first observation is that if we look at the maximum element in both A and B combined, then it is always one of the terms. It is either the maximum in A or maximum in B. So what I'm trying to say is, let's say that max of A is X and max of B is Y. So what I'm trying to say is that the element which is the maximum element of both A and B combined will always be either X or Y. So max of A comma max of B. So this is after applying the operations. Or maybe max of A concatenated with B. So max of A concatenated with B is always either X or Y. That is very obvious because wherever this maximum element ends up, it will end up either in A or B, but wherever it ends up, it will always be the maximum element of that array. So either one of X or Y will be the maximum element of both A and B. Now, the only thing which we are interested in is the minimum element. Like it is the maximum element in the second array. And what we want to do is we want to minimize it as much as possible. So without loss of generality, let's say that we have X, which is max of A plus B. And now we want to minimize Y. And also without loss of generality, we can assume that X occurs in A. So if X occurs in A, we can say that X is max of A. And now we want to minimize Y, which is nothing but max of B. So the very easy greedy strategy to do that is that for every element in B, we have two choices. Either keep it the way it is or swap it with the corresponding element in A. So our final goal is to minimize the maximum value in B. So why not minimize every value in B? So one thing which we can do is we can just take the minimum element out of AI and BI and keep it as AI. That is, if BI is smaller than AI, we will keep BI as it is. Otherwise, if AI is smaller than BI, then we will swap AI and BI. In this way, all the elements of B have been minimized, and so the maximum element of B has also been minimized. So by doing this, we can easily solve the problem, and that's the entire solution. Let's just have a look at the code now. So this is basically what I'm doing. I am taking in the input, and then I am first of all finding the minimum and the maximum, and I am always keeping the maximum in A and the minimum in B. In this way, the maximum element of A plus B will always lie in A, and all the elements in B will always be the minimum of AI and BI. And I will just sort them and finally output the maximum element in the corresponding arrays. So yeah, this is it. This completes the solution to problem A. This was not that difficult. Let's move on to problem B. Again, problem B was also very adequate for its difficulty level and for its position. So yeah, A and B were really good for their positions, but I didn't particularly like C. Anyways, let's focus on B now. So in this question, we have an array of n elements, and we can apply the following operation to it any number of times that we want, as always. So we will select some subarray of A, which is of even length. And then basically what we are doing is that we are copying the second half and pasting it into the first half. If an array has if a subarray has an even length, then obviously there is a first half and there is a second half. And basically what we are doing is we are copying the second half and simply pasting it on the first half. That's what we can do here. Our final goal is to make all the elements of the array equal. An example of the operation will be something like this. We can choose the starting point to be 1 and the length of the subarray, which is 2k, to be 4. So then the second half becomes 3, 4 and the first half becomes 2, 1. So we will just discard the first half and put the second half there. So the first 4 elements become 3, 4, 3, 4. This is an example of an operation. I hope a definition of an operation is clear enough. And our final goal is to make all the elements of the array equal. Right. Let's jump right into the solution. So to solve this problem, there is really just one main observation. So let's look at that main observation. So this is that we can never change the last element of the array. It is very obvious because there is nothing to the right of it. So there is nothing which we can copy and paste at the last position. And that is why we can never change the last position of the array. We can never change the last element. Also notice that our final goal is to make all the elements equal, and if we are not changing the last element, then the last element remains as it is, and if the final state of the array is all the elements are equal, then all those elements have to be equal to the last element only, right? Also, we have to find out the minimum number of operations to make all the elements equal, if I miss that. Right, so coming back, the main observation is that we can never change the last element of the array, so finally, we want all elements to be equal to the last element. Cool. So if you were able to do this observation, then there is a very high chance that you were actually able to solve this problem during the contest, because after this it is just a piece of cake. So let's see how we can move forward. So step 2 is that we can simply iterate in the reverse order. Let's say we are at n. So when we are at I is equals to n, we can do nothing, right? Because there is really nothing we can do. There is no index to the right of it which we can copy here. So there is nothing we can do. And now when we are at n minus 1, what we notice is that we need to make a of n minus 1 equal to a of n. So if a of n minus 1 is already equal to a of n, then we don't need to do anything. Otherwise, we are forced to do an operation with a subarray of length 2 starting from n minus 1. So what I'm trying to say is that if a of n minus 1 is equal to a of n, then we'll do nothing. But otherwise we are forced to do the operation L equals to n minus 1 and k is equals to 1. And the reason is that there is no other operation which can make a of n minus 1 to be equal to a of n. And yeah, so if a n minus 1 is originally equal to a n, we won't do anything. But if it's not the case, we will have to do this operation. We are forced to do this operation. There is nothing else we can do. So we have to increment our answer by 1 and do this operation. And now a of n minus 1 is equal to a of n. And let's see what happens when we are at n minus 2. So now when we are at n minus 2, if a of n minus 2 again is equal to a of n, we do nothing. So if a of n minus 2 is equal to a of n, we do nothing. But if that's not the case, then also we do nothing. If not, or maybe the better way to put it would be that now I have two choices. To make a of n minus 2 equal to a of n, I have two choices. So we have two choices. The two choices that we have is, first is if we choose L is equals to n minus 2 and k is equals to 1. And the second choice is, this is the first choice, and the second choice that I have is to choose L is equals to n minus 3 and k is equals to 2. Because if I do this, then a of n minus 2 will also be converted to a of n, and a of n minus 3 will also be converted to a of n if I use this second choice. So there is no reason why I should choose the first choice, because if I'm using the second choice, I am strictly getting a benefit of 2, because in using the second choice, both a of n minus 3 and a of n minus 2 are getting converted to a of n. So I will always use the second choice. So we will always choose the second choice. Now since I already know that a of n minus 3 and a of n minus 2 are surely equal to a of n, I will skip n minus 3 and I will go straight away to n minus 4. Now when I am at n minus 4, what happens is that again if a of n minus 4 is equal to an, then we do nothing. But if a of n minus 4 is not equal to an, then we greedily pick that operation that will give us the most benefit. And here, that operation is going to be something like this. So it will be more clear if I draw it out. Or maybe just, yeah. So something like this is going on. So I am at n minus 4. Yeah, I am at n minus 4 somewhere here. And a of n minus 4 is not equal to an. So the best thing that I can do is I choose this index as my starting point and perform an operation on this suffix of length 8. Yeah, so if I perform an operation on this suffix of length 8, I already know that all the elements in this suffix of length 4 are equal to a of n. So if I choose this suffix of length 8, then basically this entire suffix is going to get converted to a of n. And so that's the best thing that I can do, and there is no reason why I can't do it. So yeah, that's the only thing which I will do here. So I will do the operation like this. L is equals to n minus 7 and k is equals to 4. And by doing this operation, all the elements from n minus 7 to n will automatically get converted to a of n. And then I will skip n minus 5, n minus 6, n minus 7 and go straight away to n minus 8. And then I can keep doing this. And basically this completes the entire solution. This time I will pick that suffix of length 16. And I will pick that suffix and do the operation on it so that all the elements in the suffix of length 16 will become equal to a of n. And so by doing this in at most around O of log n operations, I will be done. But the exact number of operations will have to be calculated because I also have to skip the cases where a of I is already equal to a of n. So yeah, this way I can reverse iterate and find out the total answer. So this completes the entire solution of this problem. Let's have a look at the code now. So the code is very, very simple. What we'll do is we'll start iterating from I is equal to n minus 1. And if a of I is equal to a of n, we will just do I minus minus and continue. Otherwise, we have to increment our answer and we will pick the suffix of maximum length, and that length is nothing but every element from I plus 1 to n, and we'll just double that. So finally, all the elements from n minus I plus 1 to n. So all elements from n minus I plus 1 to n become equal to an here. And so I can skip all of the other indexes and move directly to n minus I. And I will do this while my I is greater than 0. And if I just keep doing this, I'll finally get the right answer. So yeah, this completes the solution to problem B as well. Now let's move on to problem C. Okay. As I was saying, a very annoying problem C. So the problem statement is not very difficult. What we have is we have a number n and we have a set of n numbers and they are all consecutive numbers from 0 to n minus 1. We have also been provided that n is always a power of 2. And so we have all elements from 0 to n minus 1 where n is a power of 2. And we have to find exactly n by 2 pair of elements. That is, every element has to be included in exactly one pair and every pair has to be of size 2. That is how we will get exactly n by 2 pairs. And these pairs have to be formed in such a way that the sum of bitwise and of the pairs is equal to exactly k. Right? I hope the problem statement is clear enough. If I have n by 2 pairs of the form ai comma bi from 1 to n by 2, then the summation of ai and bi for all I from 1 to n by 2 has to be equal to exactly k. And if that's not possible, then I have to just print minus 1. And the constraints are pretty standard. N is up to 2 to the 16, which is around 5 into 10 raised power 5 if I'm not wrong. And the interesting thing to note here is that k is only from 0 to n minus 1. If k was greater than n minus 1, then this problem would have been fairly complicated. But if that's not the case, then it is a very good thing for us. Yeah, so if you kind of miss reading this constraint, then this can land you in a lot of trouble. This constraint is really important here, because it is indeed possible to get to make pairs in such a way that the bitwise and even exceeds n minus 1. So we have to be careful that the constraints are like this. Okay, so I hope the problem is clear enough. Now let's try out the solution. So there is not really nothing, there is nothing much here to think about. It's just a constructive solution. You have to try different various methods to try and come up with a construction which satisfies the solutions. But yeah, there is nothing extra you can do here. You just have to think of various different creative ways in which you can make the pairs. But at the end of the day, it's basically up to you. So I'm not saying that this is the only solution that I'm going to discuss. There might be other solutions as well. But let's see my solution here. So my solution is based on 3 main observations. And they're not really observations, they are just facts which almost everyone who knows about bitwise operation knows. So one thing is that for any x and 0 is always equal to 0. The second observation is that for any x less than n minus 1, x and n minus 1 is always equal to x. This might not be that trivial to understand, and the reason for that is that okay, let's discuss the reason. Well, x is 2 raised to the power n, like we know that n is 2 raised to the power something. So n minus 1 is nothing but 2 raised to the power something minus 1. And it's a very well known thing that if a number is 2 raised to the power n minus 1, then it looks something like this. All the bits which are set form a suffix, and all the bits which are unset form a prefix. So we are just going to ignore this, and we know that any number which is 2 raised to the power something minus 1 looks something like this in the binary representation. And now since we know that any number and 1 is always that number, so if I take any number x less than n minus 1, it will have either a 0 or 1 at every position. And since n minus 1 always has a 1 in the particular position, the bits will just be the bits of x. So the bits in the bitwise and of x and n minus 1 will be nothing but the bits of x. Why? Because 0 and 1 is equal to 1 and 1 and 1 is equal to 1. So if x has 0 at a particular position, 0 and 1 is equal to 0. So if x has 0 at a particular position, then their bitwise and will also have a 0. And if x has 1 in that position, then the bitwise and will also have a 1. So yeah, this is how the second fact is proved. Also, it is kind of trivial. And now talking about the third fact, and that is in 0 to n minus 1, in the range 0 to n minus 1, every element has a distinct inverse such that so every element x has a distinct inverse, let's say x dash such that x bitwise and x dash is equal to 0, and basically x dash is nothing but the complement of x, where every bit of x dash is different from that of x. This is also kind of a well-known fact, because for any number I can just reverse its bits and nothing happens. So yeah, that's all about it. So I can reverse all its bits which are forming a suffix of it, and all those bits reverse will lead me to x prime. And obviously if I'm reversing all the bits, then the bitwise AND will obviously be 0. So for every number there exists a complement of that number, and it turns out that complement of I is nothing but n minus I minus 1. You can very easily verify this property, that complement of 0 is n minus 1, complement of 1 is n minus 2, and so on and so forth. So yeah, complement of I is always n minus I minus 1. We can also verify it because 0 is equals to 0, 0, 0, and n minus 1 is equal to 1, 1, 1. So this is being proved for 0 and n minus 1, but it will also be proved for all the i's. So for every I and n minus I minus 1, they both are complements of each other and their bitwise AND will always be 0. So yeah, this is the third observation. Now coming to the solution. So we need n by 2 pairs such that sum of their bitwise ANDs is k. So what we'll do is we will try to form one pair with sum k and all the other n by 2 minus 1 pairs with sum 0. So we will form one pair with sum k and n by 2 minus 1 pairs with sum is equal to 0. All of whom will have sum equals to 0. All of these n by 2 minus 1 pairs will have and equals to 0. Yeah. Now, how do we do that? So first of all, we will use the fact of observation number 2, that x and n minus 1 is always equal to x. So we will replace x by k, and the first thing we will do is that we will pair. So the first pair that we'll form will simply be k and n minus 1. Okay. And once we are done with that, we already have a bitwise AND of k, and now we want to form n by 2 minus 1 pairs, all of whom have sum equal to 0, all of whom have AND equal to 0. And it turns out that there is a very elegant way to do it. So you know that every element has a complement, right? So if I pair up every element with its complement, I will get exactly n by 2 pairs, all of which will have AND is equal to 0. But the problem is that I have messed things up by pairing k with n minus 1. If somehow I can fix this mess up and just come up with a algorithm which pairs up all the complements, then I will be good, right? So I already have a sum of k and I have used k and n minus 1. But what about k complement? So what I'll do is I will pair k complement with 0. So I'll pair k complement with 0. And now comes the importance of the first observation, that x and 0 is equals to 0 for any x. So if I'm pairing k prime with 0, then the bitwise AND still remains 0. And now the beautiful thing here that happened is that I have used k, I have used n minus 1, I have also used k prime, which is the complement of k, and I have also used n minus 1 prime, because the complement of n minus 1 is nothing but 0, as I have already shown here, right? And so I have already used all of these 4 values, and so all the n minus 4 values that I will have n by 2 minus 2 complementary pairs. So now I am left with n by 2 minus 2 complementary pairs. And so I can just pair every element with its complement and they will give me an AND of 0. So now we will just pair I with I complement for each leftover I. Great. So yeah, this is it. Let's try to code it up and submit it. Well, the sad part about this problem is that if you try to code it up and submit it, you will get a wrong answer. And the reason for that is that there is also a condition in which the answer will be -1. And it turns out that the only case in which the answer will be -1 is the case when n is equals to 4 and k is equals to 3. That's the only case. And what you'll notice here is that in the first step, I'm pairing k with n-1. But what if k is equal to n-1? So in the input, in the sample input, they have provided the answer as -1 for this case. So it is very tempting to just output the answer as -1 every time your k is equal to n-1. And that is what a lot of participants did during the contest. And that is why I didn't really like this problem, because it is very natural to think like this during a contest when you are kind of in between some kind of panic and you want to solve the problems as fast as possible. This is something that a lot of people must have done in the contest, I'm sure. But unfortunately, that's not the case. So if k is equals to n-1, this construction which I have done previously will fail for k is equals to n-1 because I can't pair an element with itself. So now what we can do is for n is equals to 4, obviously we know that there is no solution. But if n is not equals to 4, we know that n is at least 8. So for that, there indeed exists a solution. So first thing is that first I will pair n-1 with n-2. And the reason for that is that n-1 looks something like this and n-2 looks something like this. So the only difference between n-1 and n-2 is that of the last bit, which is 0 in n-2 and 1 in n-1. And so the bitwise AND of n-1 and n-2 is nothing but n-2. Yeah, so I know that the bitwise AND of n-1 and n-2 is equal to n-2. So now I have a sum of n-2, but my k was n-1, so I need a sum of 1 again. So then what I can do is I can pair 1 with 3. I know the bitwise AND of 1 and 3 is just 1. 1 and 3 is equal to 1. So now I have a sum of n-1 and I have successfully made 2 pairs. So now we need n by 2 minus 2 pairs, all of whose ANDs are 0. And it turns out that there is still a way to do it. So let's analyze which elements and their inverses that we have taken. So we have taken n-1, but we haven't taken any inverses yet. Similarly, we have taken n-2, but the good thing to notice here is that 3 is nothing but the inverse of n-2. As you can see, the inverse of I is n minus I minus 1. And I'm sorry. So 1 is an inverse of n minus 1. N minus 2. Yeah. So 1 is an inverse of n minus 2. I know that 1 is an inverse of n minus 2, or maybe n minus 2 is an inverse of 1. It's an equivalent way of stating it. So now I have taken n minus 1, but I haven't taken its inverse. I have taken n minus 2, but I have taken its inverse. And I have taken 3, but I have not taken its inverse. So I need to somehow take the inverses of n minus 1 and 3. Okay. We know that the inverse of n minus 1 is equal to 3. And the inverse of 3 is equal to n minus 4. So let's try to pair these up. So we will pair. So first of all, we are pairing n minus 1 and n minus 2. Then we are pairing 1 and 3. And then we try to pair 3 and n minus 4. It turns out that 3 is nothing but 0, 0, 0, 1, 1. And n minus 4. Yeah, so n minus 4 is nothing but 1. So it's 0, 0, 0. No, n minus 4 will be something like this. Yeah. Yeah, so this is n minus 4 if you talk about only 4 bits. And this is not just true for 4 bits. This will obviously be true for any number of bits. The bitwise AND of 3 and n minus 4 is always going to be 0. And that's it. We are done. So basically now we have taken n minus 1, we have taken n minus 2, we have taken 1, we have taken 3, and we have taken all their inverses as well. So now we are left with n by 2 minus 3 pairs of complements. So we can now just pair up all the complements and then get done with it, right? So yeah, this is basically the solution. This is a bit case heavy. I mean, a lot heavy. This is like really case heavy, and this should really not be a problem C, but it is what it is. So that's it. Let's have a look at the code now. So if n is equals to 4 and k is equals to 3, we will simply output -1. Otherwise, what we'll do is, first of all, if k is equal to 0, I don't know why I made this special case. It's not really necessary, so I am just going to skip it. So yeah, if k is not equals to n minus 1, what I'll do is I'll first take n minus 1 and k, then I will take inverse of k and 0. And then I will iterate and take all the elements with their inverses. This take function is nothing special. It is just, if I've already taken a or b, it just returns. Otherwise, it marks a and b as taken and it pushes them into my answer vector. And inverse is nothing but the inverse of a number, which is the number bitwise odd with n minus 1. And yeah, so this is the case when k is not equal to n minus 1. If k is equal to n minus 1, we first take n minus 1, n minus 2, then we take 1, 3, then we take 0, n minus 4, and then we iterate and take all the other complementary pairs, right? So yeah, I hope this makes sense to everyone. And if that is the case, let's move on to the last problem that we'll be discussing today. Problem D. All right. So in this problem, we have an array A of n integers, and we need to find a range of values x to y and split array A into exactly k subarrays in such a way that each of the subarray is formed from contiguous elements of A. This is thus the definition of a subarray. So we need to split the array A into k subarrays such that every element belongs to exactly one subarray. Again, the definition of a subarray. And then in each subarray, the number of elements which lie inside my range is strictly greater than the number of elements which lie outside my range. And note that this range is not provided to me in the input. I have to find this range, right? So yeah, we need to find the range such that the value of y minus x is minimized. That is, the size of the range is minimized. Y minus x is nothing but the size of the range. So we need to minimize the size of the range somehow, right? Yeah. So we need to find a range with minimum length, with minimum size, such that this third condition is satisfied. That is, I divide my array into k subarrays such that in every subarray, the number of elements which lie in my range are strictly greater than the number of elements which do not lie in my range. In the input, I have been provided with n, k, and the array. Right. So yeah, let's see how we can solve this problem. I found this problem to be really amazing. So yeah, if you were not able to solve it during the contest, I would definitely recommend to watch the solution. Okay, so let's start with the first observation. So the first observation is that if a particular range is valid, then we can always extend the range, right? So if a range is valid, then we can extend the range and it will still be valid. And the reason is very simple, because if in all the k subarrays that we have divided our array into, the number of elements which are in my previous range is greater than the number of elements which are not in my range, and if I am extending my range, then the number of elements inside my range is only increasing. It is never decreasing. And so what is positive before always increases, so it stays positive. So yeah, if a range is valid, then we can just extend it and it will still be valid, because it simply incompensates for more elements inside it. And if there are more elements in the range, then the number of elements in the range will only increase and the number of elements outside the range will only decrease. And so their difference is just going to increase. So if it was positive before, it will stay positive for all the k subarrays which I divide my array into. And so whenever you see such a thing happening, the first thing that you should think about is always binary search. That's it. If you were able to think about binary search, then Also, like if you were actually able to think about binary search, it doesn't guarantee that you will be able to solve this problem, because the binaries, even after thinking about binary search, it's not very evident how you will apply binary search, because there is no one number which you are trying to maximize or minimize. You have a range. So how do you deal with these two values, x and y? It turns out that we can binary search on the size of the range. So yeah, this is what we are going to do. We have to find a range of minimum size, right? So remember, we always binary search on the answer, and the answer is something that we have to maximize or minimize. And here we have to maximize, and here we have to minimize the size of the range, which is y minus x. So what we are going to do is we are going to do binary search on the size of the range. Okay. So yeah, this is what we are going to do. Next thing is to find a checker function. Now, if we are doing binary search on the size of a range, we need a function check of x, which tells me, which returns true if we can divide the array into k subarrays such that in every one of them, the number of elements in the range is greater than equals to the number of elements not in range. But now you might argue that we haven't defined the range at all, right? We have just defined the value x, which is the size of the range. So we can't totally define a range with its size, right? Well, yes. So what we'll do is, to find check of x, we will iterate. So in the checker function, we will iterate on the starting point of the range. And now if we have a starting point and the length, then voila, we have a range, right? So let's say we are iterating on a range I. So if the starting point of a range is I and the length of the range is x, then the ending point will be I plus x minus 1. So this becomes my range. So now I have this range, and somehow I have to answer whether or not it's possible to divide my array into k subarrays such that in every of those subarray, the number of elements which are inside this range is greater than or equals to the number of elements which are not inside this range. But remember that I have to do this in O of 1 time now. Why? Because if I am doing check of x, then I already have a log factor from binary search, and in check of x I am iterating from 1 to n, so that will give me O of n extra. And now if I take another O of n time in doing something else, then the time complexity increases to O of n square log n. So I have to check in O of 1. So we have to check in O of 1 whether the range I to I plus x minus 1 is valid or not. And also, if for any I we find out that the range I to I plus x minus 1 is valid, then we will simply return true for check of x. And check of x will return true if for any I the range I to I plus x minus 1 is valid. Great. So now we have reduced the problem to just finding out whether a particular range is valid or not. The problem was really complex, but we broke it down into pieces. First we did binary search, and that took a lot of burden off our shoulders. And then the only burden that we had was to check whether a particular size x is valid or not. And to do that, we can just iterate on the starting point, and then our range is defined. The only problem that we had was we just have the size, we don't have the range. So there is nothing to worry about. We can iterate on the starting point of the range. And now once we are iterating on the range, we have this range I to I plus x minus 1, and we somehow need to tell whether or not this particular range is valid or not. That is, if I take this range as my x comma y, will it be possible to divide the array into k subarrays such that in every subarray the number of elements which lie in this range is strictly greater than the number of elements which do not lie in this range? Okay. So now let's look at a necessary condition. A necessary condition. So the first thing we do is that in the array, if an element lies in the range, we will replace it by 1. Otherwise, replace it by -1. And the benefit of doing this is that now the problem statement is hugely simplified. Previously, the condition that we had was that the number of elements which lie in the range should be greater than the number of elements which do not lie in it. But now the condition is now simplified to the sum of all the elements in the subarray should be strictly positive. And that's the only way the number of elements in the range will be greater than the number of elements which are not in the range. So now the statement is simplified to the required condition that the sum, so divide array into k subarrays, such that the sum of each is greater than or equals to 1. Right? In the problem statement, they have mentioned that it should be strictly greater than 0. So it should be greater than or equal to 1. So as I was saying, a necessary condition is that the sum of the array should be greater than or equals to k. Why? Because I am dividing it into k subarrays and the sum of every single one of them should be greater than or equals to 1, and so the sum of the entire array should be greater than or equals to k. So this is a necessary condition. Now, how do we find out whether or not it is sufficient, or whether it is sufficient or not? Well, my claim is that this condition is sufficient. And the reason for that is that if you notice the prefix sums of this array, then the prefix sums will always either increase by 1 or decrease by 1, right? So if they are, so what I'm trying to say is that the prefix sums of the array will either increase by 1 or decrease by 1 at every index. And so what that means is that we can't jump by 2 ever. We can't jump by anything more than 1, right? So if the prefix function is taking a value which is greater than or equals to k at index equals to n, then that means it visited all the values from 1 to k. So what I'm trying to say is that if prefix sum of n is greater than or equals to k, let's for simplicity say that the prefix sum is equal to k only. So if the prefix sum is equal to k, then the prefix sum took all values from 1 to k somewhere. And the reason for that is that the prefix sum is either increasing by 1 or decreasing by 1. That is, it is not having a jump of more than 1 ever. And so it is a continuous function which takes all the values between 1 to k. Why? Because prefix sum of 0 is 0 and prefix sum of n is k. And so if it is going from 0 to k, then it is obviously taking all the values from 0 to k. And so it is taking all the values from 1, 2, 3 up till k. So yeah, so it took all the values from 1 to k. And now, if it took all the values from 1 to k, we can simply end the ith subarray when the prefix sum took the value I. Doing this, all the subarrays will have sum equal to 1. So we can end the ith subarray when prefix sum becomes I, right? That's it. So when the prefix sum becomes I, we can end the ith subarray. Doing this, we are making sure that the sum of every array is exactly equal to 1. But if the entire sum is equal to k, then it is fine. But if the entire sum is greater than or equals to k, then the sum of the last element, the sum of the last subarray would be total sum minus k minus 1. Because we are making sure that the sum of the first k minus 1 subarrays is exactly equal to 1. And whatever is left will be just put in the last subarray. So yeah, this way we can construct the subarray as well, right? So this basically completes my checker function. So as I was saying, this condition is not just necessary, it is also sufficient. So the sufficient condition to check whether a particular range I to I plus x minus 1 is valid or not is to check whether the sum of the array, which will be formed by replacing the elements which are in the range by 1 and which are not in the range by minus 1, is greater than or equals to k. But notice that this sum of array is nothing. It is the number of elements in range multiplied by 1 plus the number of elements out of range multiplied by minus 1, right? And so it is nothing but the number of elements in range minus the number of elements out my range. And so I can just pre-compute all the elements in every prefix, and using those trivial prefix sums I can find out this value, the number of elements which are in range and the number of elements which are out of range. So this is nothing but, if I compute the prefix sums, then this is nothing but prefix sum of I plus x minus 1 minus prefix sum of I minus 1. And that's it. The range was I to I plus x minus 1. So the number of elements which are in I to I plus x minus 1 can be easily found out using prefix sums. It will be nothing but prefix sum of I plus x minus 1 minus prefix sum of I minus 1. So yeah, in this way we can complete this checker function and we can complete our binary search. Once we are done with the binary search, we will have the value of our range, and then we will find out this prefix sum array, and we will construct the final solution using this algorithm. When the prefix sum becomes I, we will simply end the ith subarray. We will do this for all I from 1 to k minus 1, and then for whatever is left will be in the last subarray, and we will be sure that its sum will be at least 1. So in this way our solution is completed. Let's just have a look at the code now. Okay, so first of all I am maintaining the counts, and from counts I am maintaining prefix sums. So prefix sum of I is nothing but the number of elements which are less than equal to I, and then I start with my binary search. So here I have to check whether there is a range of size mid or not, and for that I will iterate from 1 to n minus mid plus 1, and I will calculate the elements which are in the range from I to I plus mid minus 1, and then I will calculate the number of elements which are not in the range. And if the number of elements in range minus the number of elements out of the range is greater than or equal to k, as you can see, the number of elements in range minus number of elements out of range should be greater than or equals to k. This is the condition. So if that's the case, then I am doing OK equals to true, otherwise I am doing OK equals to false. Also, I am always maintaining the invariant that right is good and left is bad. So when I'll come out of the binary search, right will be good. So then I know that right is the length of the smallest range. So I will again just iterate from 1 to n minus right plus 1. And if I find out that the number of elements in range minus number of elements outside range is greater than or equals to k, I will just do L is equals to I and R is equals to I plus right minus 1. And that is the final answer for L and R. And now I have to also divide the array into k subsegments. I can do that using prefix sums again. So I will maintain prefix sums, where prefix sum of I will denote the number of elements which lie in the range from L to R in the prefix from 1 to I. They can be constructed very easily using this line of code. And then we will just simply create our answer. When the prefix sum of I becomes I, then so if the prefix sum of I becomes I, then we will simply output prev and I, and that will be it. And whatever is left will be in the final subarray. Okay, that's it. So that completes the solution to problem C. Also, there is a slight modification here. So this should go from, that's the problem. So I should have another variable here which starts from 1, and this should be j++. And all of the rest is good. So this completes the solution to problem D. Actually, I didn't submit the code because system testing was going on. So that's it. That's the solution to problem D. Thank you for watching, and I will see you in the next video.